Okay, this is the second section of notes for Unit 1. Here we'll be focusing on the scientific method. Science is a method used to learn about the universe. There are a few things about science. First of all, it must be based on observable evidence. Secondly, it is not truth. So when someone says something like there's a scientific fact, well, take that with a grain of salt. Now, what we mean by it's not truth, it just means it's the best explanation available based on the existing evidence. So science is kind of set up to make sure that we don't repeat our mistakes as humans. For example, it used to be considered a scientific fact that the Earth was flat and that it rested on the back of a sea turtle that was supported by 4 elephants. That was a scientific fact, thousands of years ago. Well, of course, since then we have new evidence with the Greeks calculating the circumference of the Earth and the voyages of Columbus and so forth. We realize that the Earth is indeed round. Well, in the last century, we even learned more evidence. When we went to outer space and looked at the Earth, we knew, of course, it was round, but some people assumed that the Earth was a perfect sphere. But when we went to outer space, we realized, wait a minute, the Earth is actually more egg-shaped than it is a perfect sphere. So the point is that science is constantly changing or evolving as we gather more evidence about the universe we live in. Science is also designed to guard against bias. And I'd like you to take a moment to look at this painting here. This is a painting by an artist of a fox chase, and you can see those gentlemen there riding horses. And there is a bias in this painting. It's kind of interesting. And it has to do with the horses and their legs not contacting the ground. I'm going to pull up a video clip here of an actual horse racing and see if you can tell the difference. What you notice is when the horse's 4 feet are actually not contacting the ground is when the horse has all of its legs in together. See, the artist, when the artist made this painting on the left, he didn't take that into account. He used what he thought horses look like when they run, rather than looking at the actual observations of real horses running. So there was a bias in his painting. Well, see, science, we want to guard against this. When we design experiments and so forth, we want to make sure that we research and base everything on observations rather than our own gut feelings on things. Now, the scientific method, let's talk about the steps. And you may have heard about the steps of the scientific method, but we're going to review them. The first step is the objective or the question that you are trying to answer. Secondly is the background research. So you need to come up with a question that you're trying to answer, and then you research that topic so that you can make what's called a hypothesis. A hypothesis we can call an educated guess about your objective. It's a guess because, well, you're guessing at the answer to your initial question. You don't really know the answer, but it's an educated guess because, well, you've done background research. You've learned a little bit about the question you're trying to answer. So you try to make an educated guess as to what you think the outcome will be. Now, a few things about a hypothesis. It has to be testable, and we test our hypotheses with experiments. Also, it should be written in a format such as this. This is the easiest way to state a hypothesis so that it's testable. It's often called the if-then format. If I do this, then this will happen. So if I raise the temperature in my aquarium, then my fish will swim faster. That is an example of a hypothesis. You can test that by raising the aquarium temperature and measuring how fast your fish swim. So that's an example of how we can make a hypothesis. Well, now let's focus on the next step. After we make our hypothesis, you design an experiment, which is a procedure to test that hypothesis. Now, the most important thing in an experiment is to make sure you carefully select your variables. There are 3 variables in any experiment. The first one is the independent variable, and that is what's being tested or manipulated in your experiment. So in the example I gave of temperature and fast swimming fish, The independent variable in my experiment would be me changing the temperature of my aquarium. Another variable in an experiment is the dependent variable, and that's what's being measured or observed in the experiment. So again, in my example, what I'm measuring is how fast fish swim as I raise the temperature in my aquarium. So again, it's the speed of fish swimming. And that, again, is usually what we measure in an experiment. The other variables will be things called controlled variables, and these are things that are kept constant in an experiment. So in the example I gave, if I raise the temperature of my aquarium, I want to make sure I keep the same light on the tank. I want to make sure I feed the fish the same diet. I don't want to change anything else, or else that would invalidate the results. Now, as far as experiments go, there are different types of experiments you can do. One is called a controlled experiment, and that's what you can see pictured down there. This is typically done in a laboratory setting. It's controlled because there is an experimental group, which is the group that is actually being treated with the independent variable. And then there's the control group, which is identical to the experimental group except for the independent variable. So I could set up, in my example, 2 aquariums, one where I keep the temperature constant. That would be the control group. The other group, I raise the temperature to see how that affects fish swimming. That's the experimental group. Now, sometimes we can't do a controlled experiment, and we have to do what's called a natural experiment. In this type of experiment, there's no control group, and it's based solely on observations taken from a natural system. And that's what you can see the scuba diver on the right-hand side is doing. He's taking notes as he observes a coral reef. Perhaps he's looking at how much algae is growing on the reef and trying to do a natural experiment based on that. Now, the next step, once we have our experiment designed and performed, we're going to have data. Data is what we get out of it, the information collected from an experiment. So we have to analyze that data by organizing it so we can make a conclusion. Often we come up with quantitative data, which are based on numbers, but sometimes experiments will give us qualitative data, which are based on characteristics and not numbers. For example, color or something like that. Now, data is commonly organized into tables and graphs, and is usually interpreted with the use of statistics. And often in this class, you'll see I'm going to have you guys use a graphing program to make a graph, and then we can use some simple statistics to help us make a decision about our hypothesis, whether it's supported or not. And that leads into the next step, which is the conclusion. So you use the graphs that you generate from any experiment to determine whether the data support the hypothesis. So at this point, there's 2 different fates that your experiment or your hypothesis can have. If the data does not support the hypothesis, then we say the hypothesis is rejected. So, but we don't have to be upset about this because we still learned. We learned that our hypothesis is not supported. So the knowledge is still gained. And of course, our hypothesis can be changed or refined and tested again, because again, we're still learning. So if your hypothesis is said to be rejected, there's no reason to get upset. You're still learning something. Now, the other fate our hypothesis can have is that if it is supported by the data, then we repeat the experiment to confirm that support. And if it's confirmed, then we say that the hypothesis can become what we call a theory. And a theory is an analytic structure designed to explain a set of observations. So a theory in science is much different than a theory we use in common language, where we say, oh, my theory is this. Well, no, a theory is something that's been supported through observable evidence time and time again. The last step of the scientific method is to report our results. And it is important because it allows other scientists to verify our work and to build on what we have learned. And these reports usually appear in scientific journals such as the ones you see here. Science is a big journal, in science, very popular. I think we even have that in the media center. But there's more specified journals, like for example, in marine science, the Journal of Experimental Marine Biology and Ecology is one that a lot of marine scientists read to find papers. And papers are written as a typical lab report. There's an abstract, introduction, materials and methods, etc. So we'll learn more about the format of lab papers and so forth as we write lab reports later on in this class. But that does it for the scientific method notes. So make sure you get these down and are ready for our next lab.